All right, folks, we are still in Chapter 6, Normal Distribution. This is still Section 6-3, and this is video recording number 4. Okay, let's take a look at another example here, example 614. Now, what you'll see here is that it's always going to be some of these kinds of problems that use the central limit theorem. We're always talking about an X bar. We're always talking about some sort of a sample mean. So here we go. The average drive to work is 9.6 miles. Standard deviation is 1.8. Okay, so we've got the original variable is what? Make sure you can articulate this. Number of miles driven is the variable. Number of miles driven. Okay, that's the original variable. And he gives us the mu and he gives us the standard deviation. So now you take a random sample of 36. So it's n is the sample size is 36, and you want to find out what the probability. You want to find the probability that the mean of this group here. You picked a sample. So a big clue is that you picked a sample and you took a medium, or the mean of that sample, and you want to find out what is the mean of the sample. What is the probability that that mean is going to be between 9 and 10 miles. Okay, well, first thing we always do is we draw a curve, right? First thing we always do. So you draw the normal curve and we shade the desired area. Okay, now he's kind of jumping the gun here a little teeny tiny bit, but I think what he should first say is he should say I take that back. He says it right here. Okay. You'll notice up here he never says that the original variable of the drive, how far you drive to work, he doesn't say that it's normal. However, here's the thing: is the sample is 30 or larger. The sample size is 36. So you remember back up here we had the two things to remember. You can have the original variable is normally distributed, so the sample size doesn't matter. And then the other possibility is that the distribution of the original variable is not normal, but if the sample size is 30 or more, then the X bars will be normal. Okay, so let's see here. Let me find that. Okay. So we're going to draw this normal curve. We shade the desired area. We're interested in it being between 9 and 10 miles. The mean is 9.6. Okay, so here we go. This is just like we had before. Now we're going to use the properties of the normal distribution to decide what's the probability of being between 9 and 10. So the drive distance is our random variable. Our average is 9.6. This is what we're interested in, between 9 and 10. So we should be able to do this. Well, what we always did before, and we're going to do exactly the same thing, is we're going to convert these to z values. So z1, this is going to be the z value that corresponds to this x value of 9, and z2 is going to be the one that corresponds to the 10. So remember the formula? It's x take away mu divided by the yardstick, which in this case is this right here, sigma divided by square root of n. Okay, so easy calculation with your calculator. You just crank this out and you come up with two different z values. Z1 that corresponds to the 9 is -2. Z2 that corresponds to the 10 is 1.33. Okay, so now you look at the table in the back. Hopefully you've done a few of these, so you're an expert at this. So you find the two different areas, you subtract the smaller area from the larger area, and what you get is the leftover area, so to speak. It's this area to the left of this guy, take away the area to the left of this guy. So what is left over? This is left over. Okay, so you can verify the numbers on your own. Okay, that's basically what's going on here. Okay, I'm glad he wrote it this way. What he's saying here is that the probability that X bar is between 10 and 9. So x bar is less than 10, but x bar is greater than 9, is 0.8854. Okay? Okay, so now this is a very confusing subject, this central limit theorem and how to use it and so forth. And as the author says, and I agree with what he says here, students have difficulty in deciding which one do I use, okay? Do I use the z with this formula, or do I use the z with this formula? We're going to use the same table, we're going to use the same table in the back, but it's very confusing. Which one do we use? Which one of these do we use? Okay, so this formula here should be used to gain information about a sample mean. A sample mean. If you're dealing with samples and you're talking about the mean of the sample, in other words, the x bar, then you use this guy right here. Okay? This formula, this one right here, is used to gain information about an individual data value. In other words, a data point that's obtained from the population. Okay, so this guy has x bar, this guy has x, so that's your very first clue which one you should use, right? So let's take a look at this working weekends. This example actually is a good example because it uses both of the formulas, and I think that will help you distinguish, okay? All right. So be careful now. Let's read it over. The average time spent by construction workers who work on weekends is 7.93 hours, okay? Assume the distribution is approximately normal, and assume that it has a standard deviation of 0.8. Okay. So my first, I'm just telling you, take my advice. The first thing you do, make sure you can articulate what is the random variable. The random variable is how many hours worked. Boom, that's it. Okay, so we have two questions, A and B. A is find the probability that an individual who works at that trade works fewer than 8 hours on the weekend. Okay, the question B is take a sample of 40 construction workers, find the probability that the mean of the sample will be less than 8 hours. Okay, so does that make sense to you? I mean, an individual guy, we're going to use this formula. If we're talking about a sample and we're going to be talking about the mean of the sample, we're talking about the x bar, we're going to use this. Okay, so but I don't want you to just plug in formulas. You need to understand the distinction here. This is talking about an individual guy, some guy named Joe. What's the probability that Joe is going to work fewer than 8 hours? Okay. This is talking about, well, I'm going to pick a sample of 40 workers. What's the chances that the mean of that sample will be less than 8 hours? It's the same question, right? It's less than 8 hours, less than 8 hours. But here we're talking about an individual person, that you pick at random. What's the chances that that guy is working fewer than 8 hours? This is talking about what's the chances of the x bar, the mean of a sample. Okay. All right. So the same concept is, we're always going to use the z scores here, right? So first thing we always do, draw the normal distribution, shade the desired area. Okay. So the mean is 7.93. We're interested in less than 8. Okay. Is an individual person. So this is the formula we're going to use. Okay. So I'll let you crank that out. Okay. Find the area to the left. Everything is cool, right? Okay. B, same idea. We've got the normal curve. We're going to shade the desired area. Now we're going to talk about the x bars, though. We're talking about x bars. So that's why see how kind of wide this guy is? This guy's a lot less wide. It's more compact, so to speak. And the reason why is because up here, the standard deviation is sigma, whereas down here, the standard deviation is sigma divided by the square root of n. So for 30 guys, or what was the sample size here again? Let's take a look. 40 workers. Okay. Okay, so there's 40 workers, size of 40. So the square root of 40 is like 6.32 according to my calculator. So let's just say 6. So the sigma divided by 6, sigma divided by 6 is a lot less than sigma, right? You divide something by 6, obviously it's a lot smaller. So that means that this dispersion is less. It's a smaller dispersion for the x bars compared to the original x values. Okay, so now it's just all over with the crayon because you just do the formula. It's x bar take away mu divided by this standard deviation here of the x bars. And as I mentioned to you, this guy down here that, you know, any sane person would call the standard deviation of the x bars, we have a different name for it. We call it the standard error of the mean, and that was discussed on page 346. It's a little bit awkward and unfortunate in my view to have a different language like that, because what in the world does standard error mean? Why would you call it an error? Why would you call it a standard error? It doesn't make any sense. There's no errors here. I mean, it's a deviation, but it's not an error. Okay, so let's see here. I'm going to go ahead and let you verify all that. Okay. So now when you compare the two probabilities, the probability of getting an individual construction worker who works less than 8 hours is 53%. The probability of selecting a sample with a mean of less than 8 hours is 70%. Well, why is that? What's going on here? Well, this is what he says right here. This difference of 17, there's a big difference. 17% is the delta, is the difference between the 53 and 70, okay? Is due to the fact that the distribution of the x bars is much less variable than the distribution of individual data values. And then the reason is that as the sample size increases, the standard deviation of the means decreases. Okay, so here's something I think is of some interest here. This is finite population correction factor. The formula for the standard error, that's the sigma divided by the square root of n, is accurate when the samples are drawn with replacement. Well, that's craziness. Why would you replace it, right? You're talking about guys, you're asking them how many hours they work. You wouldn't replace that guy, right? Okay. Or, okay, so it's with replacement, or they're drawn without replacement, which makes more sense, from a very large or even an infinite population. Okay, so there's our escape valve. That's what makes all of this make sense. Okay, the concept is if you're drawing 30 guys out of the population of the United States, you might as well be drawing them with replacement, because it's not going to make any difference. You're drawing it from an infinite population. Okay, so there's an actual factor here. They call it the correction factor. It's necessary for computing the standard error of the mean for samples drawn without replacement, but not necessarily from a finite population. It can be from if you're drawing them without replacement, but it's not infinite, it's not a huge population, but you're still doing it without replacement, you have to do a little correction here. So there it is. There's the correction. This is something that I think it's very appropriate for you to be aware of, that there is a formula for it, but I'm certainly not going to test you on it. Okay. The concept is that if you are drawing the sample from the entire United States, you don't have to do replacement. If you're drawing the sample from even, let's say, if you're drawing it from the population of the Riverside Community College District, you don't need replacement. But if you're drawing a sample from all of the students that are enrolled in Math 12, well, maybe now you need to have a factor to correct it, because you're doing it without replacement. Well, you're not going to, this formula doesn't quite work exactly right. Okay, so here's a summary. Strongly urge you, make a copy of this, put it with your cheat sheets, put it in your notebook, because this is something that you're going to need a lot. Okay. All right, thank you. That's the end of this tape.